Sequences and summation notation. Submitted to Sir John Dustin Santos. Submitted by VILLARUEL, LEMMUEL M, AMORA, JETH Ryan S. CONVENCIDO, JUDE Andy. A sequence is a function whose domain is the natural numbers, instead of using the f of x notation. However, a sequence is listed using the n notation. There are infinite sequences whose domain is the set of all positive integers, and there are finite sequences whose domain is the set of the first n positive integers. When you define a sequence, you must write the general term, nth term or e sub n. There are sometimes more than one sequence that is possible if just the first few terms are given. Defining a sequence. There are two common ways to define a sequence by specifying the general term. General term. The first is to use a form that only depends on the number of the term, n. To find the first 5 terms when you know the general term, simply substitute the values 1, 2, 3, 4, and 5 into the general form for n and simplify. Consider the sequence defined by the general term, e sub n equals 3n minus 2. The first 5 terms are found by plugging in 1, 2, 3, 4, and 5 for n. Number 1, 3 times 1 minus 2 equals 1. Number 2, 3 times 2 minus 2 equals 4. Number 3, 3 times 3 minus 2 equals 7. Number 4, 3 times 4 minus 2 equals 10. Number 5, 3 times 5 minus 2 equals 13. Therefore, the first 5 terms of the sequence are 1, 4, 7, 10, 13. Now consider the sequence defined by the general term e sub n equals 1 divided by n. The first 5 terms are 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, and 1 divided by 5. Recursive definition. The second way is to recursively define a sequence. A recursive definition uses the current and or previous terms to define the next term. You can think of e sub k plus 1 being the next term, e sub k being the current term, and e sub k minus 1 being the previous term. Consider the sequence where e sub 1 equals 5 and e sub k plus 1 equals 2 e sub k minus 1. You can read that last part as the next term is 1 less than twice the current term. The first 5 terms are: number 1, 5, by definition. Number 2, 2 times 5 minus 1 equals 9, twice the first term of 5 minus 1. Number 3, 2 times 9 minus 1 equals 17, twice the second term of 9 minus 1. Number 4, 2 times 17 minus 1 equals 33, twice the third term of 17 minus 1. Number 5, 2 times 33 minus 1 equals 62, twice the fourth term of 33 minus 1. Now consider the sequence defined by e sub 1 equals 2, e sub 2 equals 1, and e sub k plus 2 equals 3, e sub k minus e sub k plus 1. You can read that last part as: the next term is 3 times the last term minus the current term. The first 5 terms are: number 1, 2, by definition. Number 2, 1, by definition. Number 3, 3 times 2 minus 1 equals 5, 3 times first term minus second term. Note that when k is equals to 1, the sequence gets written as e sub 1 plus 2 equals 3e sub 1 minus e sub 1 plus 1, which becomes e sub 3 equals 3, e sub 1 minus e sub 2, since e sub 1 equals 2, and e sub 2 equals 1. This is where the 3 times 2 minus 1 equals 5 comes from. Number 4, 3 times 1 minus 5 equals negative 2, 3 times second term minus third term. Number 5, 3 times 5 minus negative 2 equals 17, 3 times third term minus fourth term. Fibonacci sequence. One famous example of a recursively defined sequence is the Fibonacci sequence. The first 2 terms of the Fibonacci sequence are 1 by definition. Every term after that is the sum of the 2 preceding terms. The Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. until e sub n plus 1 equals e sub n plus e sub n minus 1. Fibonacci sequences occur frequently in nature. For example, take a leaf on a stem of many plants, like cherry, elm, or pear trees. Count the number of leaves until you reach one directly in line with the one you selected. The total number of leaves is usually a Fibonacci number. If the left and right-handed spirals on a pine cone, sunflower seed heads, or pineapples are counted, the two numbers are often consecutive. Fibonacci numbers. Factorials. The symbol for factorial is an explanation point. The factorial of a positive integer is the product of all positive integers less than or equal to that number. 0 factorial is a special case, and 0 factorial is equal to 1 by definition. 1 factorial equals 1. 2 factorial equals 2 times 1 factorial, equals 2 times 1 equals 2. 3 factorial equals 3 times 2 factorial, equals 3 times 2 times 1 equals 6. 4 factorial equals 4 times 3 factorial, equals 4 times 3 times 2 times 1 equals 24. 5 factorial equals 5 times 4 factorial, equals 5 times 4 times 3 times 2 times 1 equals 120. N factorial equals n times n minus 1 factorial, equals n times n minus 1 times n minus 2 times, until 3 times 2 times 1. Notice that there is also a recursive definition in there. Any number factorial is that number times the factorial of one less than that number. Simplifying ratios of factorials. Consider 8 factorial divided by 5 factorial. One way to work the problem would be to fully expand the 8 factorial and fully expand the 5 factorial. Here's the solution. You notice that there are common factors of 5, 4, 3, 2, and 1 in both the numerator and denominator that divide out. This leaves you with 8 times 7 times 6 in the numerator for an answer of 336. Another way to work the problem, however, is to use the recursive nature of factorials. Since any number factorial is that number times the factorial of one less than that number, 8 factorial equals 8 times 7 factorial, but 7 factorial equals 7 times 6 factorial, and 6 factorial equals 6 times 5 factorial. This means that 8 factorial is 8 times 7 times 6 times 5 factorial. So, 8 factorial divided by 5 factorial is 8 times 7 times 6 times 5 factorial divided by 5 factorial is equal to 8 times 7 times 6 equals 336. The point is that there is no need to multiply the entire thing out when you're just going to be dividing a bunch of it out anyway. Here are some steps to simplifying the ratio of two factorials. Number 1. Find the smaller factorial and write it down. It won't change, and it will be the part that is completely divided out. Number 2. Take the larger factorial and start expanding it by subtracting 1 until the smaller number is reached. Number 3. When you reach the smaller number, write it as a factorial and divide out the two equal factorials. Here's an example with a little bit more complicated ratio. Since 2n-1 is less than 2n plus 1, copy the 2n-1 factorial down on the bottom. Now, take 2n plus 1 times 1 less than 2n plus 1. 1 less than 2n plus 1 is 2n plus 1 minus 1 equals 2n. Take that times 1 less than 2n, which is 2n minus 1. Since that 2n minus 1 is the same amount on the bottom, call the 2n minus 1 factorial and then divide it out, leaving the product of 2n and 2n plus 1 as the answer. Here's the solution. Sigma/summation notation. Summation is something that is done quite often in mathematics, and there is a symbol that means summation. That symbol is the capital Greek letter sigma, and so the notation is sometimes called sigma notation instead of summation notation. The k is called the index of summation. K equals 1 is the lower limit of the summation and k equals n, although the k is only written once as the upper limit of the summation. What the summation notation means is to evaluate the argument of the summation for every value of the index between the lower limit and upper limit inclusively and then add the results together. Cardinality. We define cardinality of a set as the number of elements in the set. We can extend this idea to infinite sets. The sets E and B have the same cardinality if and only if there is a one-to-one correspondence from E to B. A set that is either finite or has the same cardinality as the set of natural numbers is called countable. A set that is not countable is called uncountable. Cardinality of set of natural numbers. An infinite set is countable if and only if it is possible to list the elements in a sequence indexed by the positive integers y. E one-to-one correspondence F can be expressed in terms of the sequence E sub 1, E sub 2, E sub 3 and so on, where E sub 1 equals F of 1, E sub 2 equals F of 2, etc. One-to-one correspondence for set of odd positive integers. In terms of positive integers, F of n equals 2n minus 1. Countably infinite. Elements can be listed. Anything that has the same cardinality as the integers. Example, rational numbers. Ordered pairs of integers. Uncountably infinite. Elements cannot be listed. Example, real numbers.